Welcome to Calculus. Fractions will pop up when you least expect it. On this episode, Stevenson will demonstrate
In the last set of videos, we talked about how we can compute areas and accumulations by reversing differentiation, and we called that anti-differentiation. Newton actually discovered this in 1666, and then Gottfried Leibniz discovered a few years later. The only difference, though, is Newton kept it to himself and Leibniz published it. And in terms of publishing, what that then does is it brings other mathematicians and scientists into it, and then now you can continue to further the progress of what they've learned. So this connection between areas and accumulations and anti-differentiation is called the fundamental theorem of calculus. It's important to really remember this is a theorem about integration. And so, as long as you're working with continuous functions, there's actually two ways of thinking about the definite integral. Think of it as the limit of Riemann sums or the change of a value of an antiderivative. So there's two aspects that we have with the fundamental theorem of calculus. We have the evaluation part and we have the antiderivative part. So let's look at the antiderivative part first. So if f is continuous on a closed interval a to b, then our function f of x is the integral from a to x of f of t dt. It's going to have a derivative at every point x that's in that closed interval. And then we have this relationship. So let's break this down. So remember, capital F, that's your accumulator function, right? Okay, and then remember, what does it equal? That equals the capital F of x minus f of a when you do the integral on the right-hand side. Now, df dx, or d capital F dx, that is your derivative of your accumulator function. Remember what that is. That's just the derivative of the definite integral. And the little f of x, that's the integrand evaluated at the upper bound. We talked about briefly in the last one how there's this relationship between derivatives and antiderivatives. And that's what this is essentially showing us. Okay, so this equation is very important. Okay, it's very powerful. Every continuous function will have an antiderivative. And what this says also is that integration and differentiation are inverses of each other. So let's look at an example. I want to demonstrate to you this relationship of taking the derivative of an integral. Okay, because we have to think of them as inverses. So suppose you wanted the accumulator function of the integral from 0 to x of cosine t dt. Well, we know f of t is cosine, so we're going to use the antiderivative of that, which is sine. So if we take that and we rewrite what we're doing here, we use what we learned in the previous set of videos, the previous lesson, that we know the accumulator function of this is essentially f of x minus f of 0, or capital F, right? So that would be sine of x minus sine of 0. So now what we know is the integral from 0 to x of cosine t dt is really sine of x minus sine of 0. So now let's take the derivative of this accumulator function we just created. So we're basically doing this, d dx of the integral of 0 to x cosine t dt. So in doing so, we're really taking the derivative of sine of x minus sine of 0. Well, sine of x, the derivative is cosine. And sine of 0, that's a constant. The derivative of a constant is 0. So notice our result here at the end is just the integrand it's just the integrand evaluated at the upper bound. Because the derivative is undoing the effects of the integral, which essentially is finding the antiderivative. Okay, remember they're going to be inverses of each other. Now, what about chain rule? Remember, every function's really a chain rule problem, right? We've talked about that a lot. So how do we then apply this antiderivative part of the fundamental theorem of calculus with chain rule? Well, let's take the previous example and let's modify it a little bit. So let's find the accumulator function of the integral from 0 to x squared of cosine t dt. Again, f of t is cosine, so its antiderivative is sine, and I'm going to denote the antiderivative by capital F. If I want the antiderivative of this function, I would do capital F evaluated x squared minus capital F evaluated at 0. And that would give me sine of x squared minus sine of 0. Now, let's do the derivative of that. Ready? So we're doing the derivative with respect to x of the integral of 0 to x squared of cosine t dt. So that means we're doing the derivative of sine of x squared minus sine of 0. Well, sine of x squared requires chain rule. So that's really cosine x squared times 2x. And remember, the sine of 0 is just 0 because that's a constant. Do you notice a shortcut? How could you get that answer, cosine x squared times 2x, if you're given the derivative of that? Do you notice that the result here is really just the integrand evaluated at the upper bound multiplied by the derivative of the upper bound? So this is another way in which this antiderivative rule is applied. Okay, and remember, the derivative of the integral is just the integrand evaluated at the upper bound times the derivative of the upper bound.